Welcome back, and we're going to look at the second part of last part of our HL atomic structure. And this is looking at successive ionization energies and what it can tell us about the structure of an atom, rather than just calculating the first ionization energies. So this is going beyond our first ionization energies and what it can tell us. So while the first ionization energy tells us a lot about the atom structure, there are many atoms that can form ions which have different charges. So what we have is what we refer to as we go past that first ionization energy, because it is the energy for the first mole of electrons. As we go, we will see successive ionization energies which get greater. Okay, so when we plot this, we can get information about the overall structure of the atom. So this is what we see here, in that we have plotted the successive ionization energies for aluminium. Okay, so we can see here that we have 3 that have the lowest value of energy down here. Okay, so 1, 2, 3, which correspond to the valence electrons. Then we have a large jump. Then what we see is a 4 more with increasing between each one to the highest one up here. Okay, so if we have a look here, this is the number of electrons removed. So we've got the first, second, third, and then we jump. So when we look at the electron configuration of aluminium, which when we're doing these questions we should always look at, so in this case we can write 1s2, 2, 2p6, 3s2, so we've got 10, and we want to get to 13, so this is now 12, and then 3p1. So what we're seeing is the first ionization energy. Okay, remembering we're going to be removing our 3p1, which will be the easiest to remove. Then we're going to have the s, which are a little bit closer in. Okay, remembering that the s orbitals are a little bit closer in because s is lower in energy than p. So these are going to be a little bit harder to remove. So we've got our 3s and the other 3s from here. Okay, when we have removed these 3 outer valence shell electrons, we actually move into the second shell. Okay, so we've now removed these ones. We're now moving into the second shell where we have the 2p electrons. And this one only shows the removal of 7 of the electrons, but you can see here that now we have a big jump, and this is moving to the next shell. Okay, so as we move to the next shell, there is a large jump in energy as we get closer to the nucleus. These electrons are more tightly held, so they require more energy to remove. Then each successive one will, of course, take more energy as we go through our 2p electrons into the 2s. And then eventually the 1s, there would be another much larger jump, where we see our highest ionization energy levels because those 2 electrons are very close to the nucleus. So we see this pattern through all atoms, and this gives us evidence for Bohr's idea that shells are energy levels within an atom. Okay, so we've talked about this in periodicity before and atomic structure, that these energy bands that we see in the successive ionization energies of atoms indicates that there are distinct energy levels within an atom, which is support for Bohr's model of the atom. Key thing with these to remember is that when you're looking at these ionization energies, it is a logarithmic scale. Okay, so it's a log 10 scale. So much like pH, each successive one is actually 10 times more than the one previous. Okay, when we're looking at a logarithmic scale. So these values, while they look small, are quite significant in terms of energy. We start with the valence will be the lowest moving closer, and then as we go, we get closer to the nucleus. So this is the kind of question that we're going to see. We see this question here. It says a graph of some successive ionization energies of aluminium is shown in figure 2.26. Explain why there is a large increase between the 9th and 10th ionization. And then it wants us to explain why increase between the 6th and 7th values is also greater than the increase between the 5th and 6th. So generally what you need to do with this is pay attention to where it says some successive ionizations. The graph that we've been shown below actually shows all 13 electrons for aluminium. However, sometimes they will just show you a portion of it, and you need to work out where in the graph you're actually looking. So if we look at the graph that we've been provided, we can see that they have shown the 3 valence electrons, the 8 second shell electrons, and then the 2 first shell here in terms of ionization energy. So we need to explain why there is a large increase between the 9th and 10th. Okay, so this is 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, and 10th. Okay, so why is there an increase here? And also the increase between the 6th and 7th values is greater than the increase between the 5th and 6th. So let's have a look at the way that they have structured these answers. So you'll notice here that there's a couple of things that they're including in their explanations. A, they are giving the equation, okay, for the ionization from the removing going to an 8 plus. Okay, remember the first ionization energy is going from neutral to 1, so the 9th ionization energy is going from 8 to 9. So remember, it's in a gas. We're removing the electron, so we get the electron as a product. So they've given the equation explaining the ionization that they're talking about. They have then given the configuration for the ion. So this is showing that it has a 1s2, 2s2, 2p1 after losing the number of electrons. Then the electron is removed from the 2p orbital. Okay, and then when we look at the 9 to 10, okay, we can see here that the ion is a 1s2, 2s2, so the electron is removed from the 2s orbital. So you'll notice when answering these questions, they are giving the electron configuration to show which orbital the electron is located in. Then the explanation comes about that the electrons in the 2s orbital will be of lower energy, so they're closer to the nucleus and experience a stronger effective nuclear charge. Okay, so they're more difficult to remove. The 6 ionization energy we're going to look at in the same way. We've given the equation that it corresponds to the charge from 5 to 6. They give the configuration 1s2, 2s2, 2p4. Okay, the electron is removed from the doubly occupied 2p. Okay, so they've looked at the x, y, and z orbitals, remembering that the metro rule, they stay single and then they go back and double up. Okay, so the 7th ionization energy corresponds to the 6th to the 7th, and then the electron is removed from the 2p orbital. They've then used Aufbau diagrams to explain this, in that the doubly occupied orbital is repelled by its partner. Okay, so when the electrons are paired up, they have a slight repulsion. So it is easier to remove than the half-filled orbitals where we have one in each of the p orbitals, because this is more stable. So in this case, the paired electron will require a bit less energy to remove than if the single electron. Okay, so it's easier to remove because of that repulsion of the pairing. So when you're answering these, remember these are HL level questions, so you want to make sure that you are supporting your answers with the electron configurations and the understanding of the Aufbau diagrams and orbital structures. When we go back to looking at the first ionization energy of the elements, we know that we see an increase in the ionization energy as we move from left to right. This, of course, being because we have an increased electrostatic attraction to the nucleus due to an increasing effective nuclear charge and a decreasing atomic radius. So the noble gases, as we move across a period, will have our highest first ionization energy, and then we go back and they drop back down as we go to the first element in the next period. If we look at this in detail as we go across a period, however, we will notice that it is not a continual climb of ionization energies, that at different points we see it dip back down again, and then we appear to have outliers. These, of course, can be explained due to the extra stability that we see in different configurations of our subshell. So as with the questions that we were talking about earlier, what you really want to do is be able to look at your electron configurations for each one. So if we start with lithium, which is the first of our second period, we're going to have 1s2, 2s1. Then with beryllium, it'll be 1s2, 2s2. And then we're going to see boron drop down with 1s2, 2s2, 2p1. Okay, so this one has come a little bit further out, but it's unpaired. We're now a little bit further out, so we can see the energy drop with some extra stability. Carbon, nitrogen is higher in energy than oxygen, which drops back down, and then we move successfully from across here. So if we combine this with what we were talking about before with our successive ionization energies for the way in which we answer questions, let's have a look. So we're given this question here, which we were talking about before, where the idea that the existence of subshells can, just like shells with Bohr's model, the existence of subshells can look at first ionization energies to talk about stability. So let's look at question 1. In period 2, there is a decrease in first ionization energies between beryllium and boron, and in period 3, there is a decrease between magnesium and aluminium. Explain this decrease in ionization energies between group 2 and group 13 metals. Okay, remembering groups, we're now in group 2 and group 13. Think about what happens between the effective nuclear charge, ionic radius, and things like that as we go across. Question 2 then asks us, in period 2, there is a decrease in first ionization energy between nitrogen and oxygen. And this is seen again in period 3 with a decrease between phosphorus and sulfur. Explain the decrease in ionization energies between group 15 and group 16 elements. Let's have a look at the solution so that you know how to approach these and look at the practice questions. So here we are setting up the way that we're going to answer. Group 2 elements have the electron configuration NS2, remembering that the outer shell valence electron configuration is the same within a group. Okay, so within a group, it's always the same. So everything in group 2 will have their valence shell electrons in the S2 subshell. In group 13, we have an electron configuration which has NS2 and P1. Okay, so we've got the filled S and the half-filled P here. So the electron removed when the group 13 elements is ionized is a P electron, whereas for the group 2, it is an S electron. Electrons in P orbitals are of higher energy and further away from the nucleus than the S, so they are easier to remove than the electrons in the S orbital. Remembering that the ionization energies that we looked at before were starting at the lowest, meant that these were the valence electrons, okay, and then going up. Now we're not looking at within, this was an individual atom. We're looking across a trend in a period. So even though it may be overall higher as we go across, we need to look at these for which would be the valence, because our valence electrons are going to be less tightly held. Okay, so within the same atom, they're going to be our lower energy ones for the ionization energy. So then when we look at the group 15, we look at our configuration, so NS2, and then we're going to have P3. So each one of these will be in one of the individual PX, PY, or PZ orbitals. Okay, whereas when we look at 16, we now have our S2 and then P4. So we will have 2 in the PX and then 1 in each of Y and Z. So one of them will be paired. So for the group 16, it's going to be a doubly occupied or a paired. You could even use your AFBOW diagram. Your AFBOW diagram showing the pairing of the electrons to support this. And therefore, because of that repulsion from its partner, it will be easier to remove. So we're using the same kind of arguments here as we were for successive ionized energies, looking at the first ionization energies as we move across a period or down a group. That's it from me for our ionization energies. Now it's time for you to have a look at a couple of these questions and practice justifying them. Remember to always make sure you justify your answers with a look at the electron configuration, including your subshell notation, so you can justify according to whether or not the electrons are in SP or even paired up. And that's it for atomic structure higher level.